Hello everyone, my name is Christopher Ademadanso. Welcome to our presentation on I/O organization in computer systems. Today, we'll dive into how computers communicate with external devices like keyboards, printers, and storage systems. Input-output, or I/O, is the process of exchanging data between a computer and these devices. Think typing on a keyboard as input or displaying text on a monitor as output. I/O organization is the structured way computers manage this data transfer to avoid slowing down the CPU. Without it, systems like ATMs or biometric devices in Ghana would be inefficient. In this presentation, we'll explore key I/O techniques such as programmed I/O, interrupt-driven I/O, and DMA, as well as I/O mapping and real-world applications in Ghana. Let's get started.
Hello everyone, my name is Joshua Jemfi Ntiamwa, and in this video I'll be explaining why input or output organization is important in computer architecture. So first, let's talk about the speed mismatch between the CPU and the input or output devices. The CPU operates really fast, usually in nanoseconds. For example, a 3 GHz processor can complete a cycle in about 0.33 nanoseconds, but input or output devices like hard drives work much slower in milliseconds. This creates a big gap in speed. If the CPU has to wait for the input or output device, it ends up doing nothing, wasting valuable processing time. That's where input or output organization comes in. It helps manage this mismatch. Instead of making the CPU wait, the system can use techniques like buffering and interrupts to keep the CPU productive while input or output operations happen in the background. Next, we also have different types of input or output devices with different behaviors. For example, a keyboard sends data only when we press a key, and that's sporadic. But hard drives continuously read and write data. These are very different ways of working. So, input or output organization helps tailor the communication between the CPU and each device, depending on how the device behaves. In short, without proper input or output organization, the CPU was stuck waiting for slow input or output devices. But with good input or output handling, we keep the CPU efficient and make the system work smoothly. Thank you.
My name is Onismo Sampa. I'm from Group 10. I'm here to present on the program input and output devices. So, what exactly is program input and output devices? Think of it as a simple but not so smart way the CPU talks to the devices of connected to the computer, like the printers, the input, the normal input and output devices. So here's how it works. In this method, the CPU literally keeps asking the devices over and questions it over again. For example, it will keep checking the keyboard. Any key pressed yet? If no, it keeps asking again and again and again. This constant checking is what is called polling. Now let's move on to the advantages of program input and output devices. The good side to it is that it is very simple to implement. No hardware, no extra hardware is needed, and it works fine for very basic or low speed systems. So as you know, every good thing has a bad side. So the disadvantages of the program input and output devices is that while the CPU is busy doing the constant checking, it is wasting valuable time. Instead of performing other useful tasks, it's stuck in a loop just waiting for what the device. And that's why, to me personally, I think the input and output devices is considered to be inefficient.
Hello, my name is Angelia Nanamareko, and I'm going to be presenting on the interrupt-driven I/O and how it works, the advantages, and real-world examples. How it works. So a device known as an input output device, which can be like a printer, which sends and receives data and information, would send an interrupt signal when ready. The CPU will pass current task, handles IO, then resumes. Example, the keyboard sends interrupt on key press. Basically, this is trying to say that when you have a printer, for example, and then you issue a command into the printer, while the printer is working, you can get a prompt from an already ongoing application on your computer. And then the CPU is going to prompt you so that you are able to move from the first task you were doing to do another one at the same time. The advantages: the CPU performs useful work instead of polling, and it enables multitasking. Example, typing while downloading. So as I said, you can be downloading a file and at the same time typing, or you can be using a printer at the same time surfing the internet. Real world examples, we have Ghanaian ATMs use interrupts to process and swipe instantly. So when you go to the ATM, which is um, very common in Ghana, you are able to use your card to swipe, and then you're able to um, key in your data at the same time while the card is going through at the bank. So these are my few points that I have presented. Thank you.
And I feel I'm start presenting on direct memory access. Okay, so how it works. Okay, so the direct memory access controller transfers data between the memory and devices without CPU. So with the direct memory access, you don't need the you need a CPU, but you don't really need a CPU in transferring the data. You just need a CPU to show you the location of where you're supposed to transfer the data to and from. Yes. CPU initiates transfer and then direct memory access handles it. As I said, the CPU only tells you, say, it's moving from the device onto the RAM or the memory. When transferring, the CPU is not involved. It's a direct memory access that does the transferring. Okay. Advanced advantages of direct memory access: fast data transfer for large data sets. Yes. So, for example, let's say you're downloading a very big, a very big file, which is like 20 gig. A direct memory access is the best way to do that because with a CPU, it's just, with a CPU does everything. So it will be slower. To be slower. Say you have something doing in the background. Say you're downloading something in the background. If you're also downloading the data you're transferring, it will be slower because of what you're doing in the background. But with the direct memory access, it can do it faster because it's mainly for that. Yes, it reduces CPU workload and improves system efficiency. Yes, so it reduces what the CPU has to do. It's like maybe the CPU is downloading a movie for you, like it's 2 movies for you, and you're also transferring a file. That's 3 taxes. So with the direct memory access, you don't need to do all these three. You need to do only two, which is the download of the movies. Yes. Okay. For an example is copying files from USB in Ghana Cafe uses direct memory access for speed. Yes. When I'm transferring a file from a USB onto the RAM or the memory, you need a direct memory access. Yes, it's a direct memory access that does the transferring, not the CPU, the direct memory access.
Hello everyone, my name is Christopher Ladamada, so let's explore input-output mapping. IO mapping is how computers address devices like keyboards or printers. In memory mapped I/O, devices share the same address space as the RAM, so the CPU uses standard memory instructions to communicate. For example, in Ghanaian ATMs, the card reader's status is read like a memory location, making programming simpler but using up RAM addresses. For example, if your RAM has 1,000 memory spaces and then gives out 100 of them to different devices such as printers, scanners, keyboard monitors, etc., you have about 900 memory spaces left. So even though it makes programming simpler since it uses standard memory instructions, it is still using up the memory spaces that your RAM has, making it limited. In contrast, isolated I/O gives devices separate port addresses, accessed with special instructions like in older computers. This is more secure but complex. Secure in the sense that a person can't get access to your devices using your RAM because they do not share the same memory location or memory spaces. But it is complex since you can't use memory instructions. You have to use special instructions to maneuver your way around it. Most systems in Ghana, like biometric scanners for voter registration and ATMs, use memory mapped I/O because of its ease of use and speed. Thank you very much.
Yes, I'll be talking about I/O models. That's the bridge to devices. So this bridge is like something that connects the CPU to the external devices, and the bridge is made up of I/O controllers, system bus, and then the ports. The I/O controllers they manage specific devices, yeah, like the USB. Then the system bus they just wires that connects the CPU, connects from the CPU to the ports, yeah, and then the ports are just physical interfaces that accepts peripheral devices like the USB, yeah, and this is how they work. So the CPU send commands through the system bus. Yeah, like I said, there are wires send digital commands through the wires to the I/O controllers. The system bus, the there's the address bar, data bar, and a control bar. Sorry, address bars, data bars, and a control bars, depending on what the command is. Yeah. So, for instance, when the CPU sends a read command, it passes through the control bars, and then when it sends an address command to request an address from the memory, it uses the address bars. And for instance, when you type something on the keyboard, whatever you type passes through the data bus. Yeah. So it's simply that IO models the bridge to devices that the bridge that connects external devices to the CPU. Yes, that's all.
My name is Sylvester Mohammed. I'm going to be talking about the why IO organizations matter. That's to say the benefits of information output system organizations. So the first one is minimizes the CPU idle time. So the idle time is more or less like the time in which the CPU functions less or does not function at all. So faster system performance. So one of the advantages of the IO system organizations is that it fastens the system's performance. The second one is it supports multitasking. That's to say, um, runs multiple programs simultaneously. So modern IO system organizations allows the methods allows you to handle multiple operations concurrently, improving the overall system performance. So the third one is it enables real-time computing. That's critical at ATMs, medical devices, and Ghanaian biometric. So that's just an example of real-time computing. Where we are made to understand that real-time computing refers to the systems that must respond immediately or strictly to instructions sent to them within a period or time frame. So impacts on modern computing. So what are the impacts of IO system organizations? on modern computing. So it ensures reliability in high demand environments such as banking systems and other systems. These are systems you could really rely on when it comes to those functional sectors of the economy or life as a whole. So it also enhances user experience with seamless device interaction. And when we talk about seamless device interactions, it means real-time computing eliminates noticeable delays between user actions and system responses. That's when you click those stuff, click, double click, and those stuff. The grace period or the time period between which the system takes to undertake action sent to it. You get. So this is basically what the points on the slides briefly means. Thank you.
Name is Daniel Elom, and I'm here to talk about the real-world application under IO organization. So a real-world application simply describes applications which are normally used in the real world, and I'm here to talk about at least 3 applications which are used in the real world. So the first application is an automated teller machine. This automated teller machine uses interrupt-driven IO for instant transaction response. What it means is that instead of constantly checking polling for inputs like card insertion or PIN entry, ATMs use interrupts which notify the processor only when an action happens. It is useful because it improves speed and efficiency. The CPU doesn't waste time checking the card slots, it waits until it's interrupted. This is for faster response and time during time. This is for faster response during time during. This is for faster response when it's time for maybe withdrawal of money or deposits or balance checking. And next one is biometric systems, which is fast IO or for voter registration and ID verification. These systems need to quickly read and match data like fingerprints or facial scans. Fast IO allows data to be captured and processed almost instantly, improving throughput in high traffic environments. Where it's used is national ID systems, e-voting registration, airport immigrations, and many more. So these biometric systems are mainly helpful because they are much more faster and efficient in terms of security reasons. Because nowadays there are a lot of scammers in the system and they are able to track down people's security codes and a lot of things, which is very bad to the system. So they brought this biometric system for much more efficient security system. And the last one is point of scale, which is normally short point of scale devices, which is normally shortened as POS. This uses DMA for quick payment processing in markets. What it means is that the full meaning of DMA in the first place is direct memory access. This allows data to be transferred between devices, especially card reader or barcode scanner. A memory involving the CPU. Why it's efficient is that it frees the CPU to handle other tasks while data is being moved, which speeds up overall system performances. It is faster to check out experiences in stores and markets, less lag in payment or receipt generation. So in conclusion to all of the IO organization and in all what we've said throughout our presentation, we've explained how computers interact with external devices, the different methods like program IO interrupt and DMA, and how hardware components make everything work smoothly. Without IO organization, modern computers wouldn't be fast as reliable. Thank you for your time, and we hope you now understand how input and output organization works in computer systems. Thank you.